Hello everyone. Tonight we're going to explore many different chemical elements, their properties, their abundance or their rarity, their relevance in everyday life. Some are very famous and others are little known, but they are all interesting to discover. I will also tell you about the periodic table of the elements that we are going to follow and detail in our systematic exploration. And I will explain plenty of other things about what distinguishes elements, their atomic structure, how and why they combine to form molecules and chemical compounds. We will see where they are found and how they are used in industry or research. So we have a lot to discuss. Now, please make yourself comfortable. If you would like to try a different take on science stories like this one, you can already find some on Lights Out Library and La Biblioteca de los Sueños, which are podcasts and YouTube channels with my stories retold by Olimpia in American English and in Spanish, respectively. You will find links to them in the description. As always, I also invite you to listen on Spotify, Apple Music, and other audio platforms if this is more convenient for you. And you are also as welcome as ever to support this channel on Patreon. It gives you access to downloads. You can stream all stories too, with or without background sounds, and it really helps keep me going with new stories, because I try to minimize advertising on all platforms, as much as YouTube lets me, at least. I also avoid sponsorships to not force more commercial pressure on you with products that I'm sure you don't need. So I rely on your voluntary support to fund this channel, if you wish. And now, let's get started with the first element, hydrogen. Hydrogen is thought to be the most abundant chemical substance in the universe. It certainly is in our galaxy. It is estimated that roughly 75% of all matter in the universe would be hydrogen. And this element could be called the simplest of all of them, because it is the lightest and its structure is simpler than others. What does it mean? To understand what a chemical element is, we need to talk about the structure of atoms and what makes an element different from other elements. As you know, all atoms have a nucleus made of at least one proton, a smaller particle. Another type of particle, very similar, that are also found in this nucleus are neutrons, and to this nucleus are bound one or several electrons that change place very fast and form like a swarm around this nucleus. This is what an atom is like, and what defines an element in the periodic table is the number of protons in its nucleus. This number of protons is called the atomic number. Hydrogen has one proton, so its atomic number is 1. If it had 2, which happens when two atoms of hydrogen merge when they fuse, it would no longer be hydrogen, it would become helium, the element with the atomic number 2. As you also know, atoms are not the smallest possible units of matter we know of. They are made of smaller particles. We just talked of protons, neutrons, and electrons. And these particles are themselves made of even smaller bricks, smaller units. Atoms can gain or lose particles. They can be broken sometimes, or forced to merge, even though it takes a lot of energy to do that. So they are far from being a primary unit of matter. They are made of different, smaller bricks. So what makes the atomic level that relevant in that case? Why do we look so much at atoms when we speak of matter? First, because atoms happen to be a very frequent and stable type of organization of matter. Not all of matter is organized, structured in atoms in the universe. There are also free particles, but the bulk of matter we know of is structured in atoms. And another thing that makes atoms very relevant is that all elements appear with the atom. Under it, when subatomic particles are not structured as atoms, there are no elements. All the elements we know of, from hydrogen to the heaviest atoms, have certain properties that distinguish them because they are structured as they are as atoms. Hydrogen, gold, iron, or uranium are made of the same basic particles. They are differentiated and have these different properties, including their appearance, their mass, their capacity to react with other elements, only because they are atoms. This is actually how an atom is defined. Atoms are the basic particles of chemical elements. We will see a lot more about atoms and how they interact. But to go on with hydrogen, why is it the most abundant element in the universe? It is believed that the early combination of particles into atoms after the appearance of our universe, after the Big Bang, created essentially hydrogen atoms. The formation of protons, which are the nuclei of hydrogen, occurred almost immediately. It is believed in the first second after the Big Bang. But it took much longer for these protons to get associated, to get bound with an electron, which made them electrically neutral. Both particles, proton and electron, are electrically charged with opposite signs. So when an atom has the same number of protons and electrons, it has no net positive or negative charge. It is electrically neutral. But at the start, just after the Big Bang, it is believed that matter was too hot for electrons to remain bound to protons. First, it needed to cool down. And only after this cool down, at a time estimated to be 370,000 years after the Big Bang, electrons and protons would have begun to bind and stay stuck together. So the first atoms would not have appeared with the universe itself, but rather a few hundreds of thousands of years later, when the original heat, the extreme concentration of energy, had receded enough for atoms to appear and remain stable. At first, all atoms would have been relatively light: hydrogen with 1 proton, helium with 2, and lithium with 3. All the other heavier atoms or elements with more protons, more particles in their nuclei would have appeared later and be the product of ulterior fusions between these smaller atoms, especially hydrogen. We will also elaborate on this later, and I will tell you how other elements would have formed. But why is hydrogen called like that, by the way? Hydrogen comes from Greek, and it means water former or water creator. The name appeared after it was discovered in the 18th century that this gas, because in standard conditions on Earth, pure hydrogen is a gas, that this gas could burn or explode and produce water when it was put in contact with air, more exactly the oxygen in the air. When something burns or explodes, it is in fact a chemical reaction. And this is what is happening here. The chemical reaction in which hydrogen and oxygen get recombined between them into a molecule called H2O, 2 atoms of hydrogen and 1 of oxygen, better known as water. Hydrogen got its name from it, its capacity to produce water when it reacts with oxygen. There could be a lot more to say about hydrogen, but let's move to a second element, the element with atomic number 2, with 2 protons in its nucleus, helium. Helium is not very present in our daily lives, contrary to hydrogen, which is a big component of our bodies. But don't underestimate helium, because at the scale of the universe, it is a big deal. About 24% of the total elemental mass in the universe is helium. I told you before that hydrogen was by far the most important one, with close to 75% of all elemental matter. So with these 2 elements, we already have close to 99% of the elemental mass in the universe. The bulk of matter consists of hydrogen and helium. Helium is very present in stars. It is the product of nuclear fusion in stars. You know that the fuel of stars during most of their lives is hydrogen. Inside the stars, under extreme conditions of temperature and pressure, nuclei of hydrogen atoms are forced to merge, and when they merge, this fusion liberates a lot of energy. This is what stars live on, and the product of this fusion is a new helium atom, an atom with 2 protons in its nucleus. So there's a lot of helium inside stars, and the more a star ages, the more helium it accumulates. Apart from stars, helium is also a big component of gas planets, like Jupiter or Saturn. On rocky planets, like Earth, Mars or Venus, it is present only in small quantities. At normal conditions of temperature and pressure, at standard conditions, it is a gas that is light, colorless, odorless, non-toxic, and a well-known use of its lightweight is when it is used as a lifting gas in balloons or airships. other than that, helium is used in different industrial processes at a very low temperature, low enough to be liquid. It is used in cryogenics, the science of very low temperatures, close to absolute zero. It also serves to cool electromagnets, to pressurize environments, or to make silicon wafers. Wafers in electronics are thin slices of semiconductors. The wafer serves as a substrate for microelectronic devices that are built in and upon the wafer. The largest reserves of helium on Earth were found in natural gas fields, especially in the US, which is the largest supplier of this gas today. One thing helium is famous for is that it is called a noble gas, together with other gases that are grouped with it in the periodic table: neon, argon, krypton, xenon, or radon. As we advance, I will tell you about the logic of the periodic table, because it is much more than a list of elements. It also tells us of their properties, and it groups elements between them. Noble gases are one of these groups. There are 18 different groups in total, and elements within these groups share similar properties. For example, all noble gases are odorless, colorless. They all become liquid at very low temperatures, and they are called inert because they have a very low chemical reactivity. They typically don't react with other elements. Why don't they? This is because of the configuration of their electrons. The number of electrons in atoms and the way the swarm of electrons around the nucleus is arranged is a big factor that determines reactions between elements. When elements react between them, which means new molecules or new compounds are formed or destroyed to be replaced with others, atoms share their electrons or gain and lose them. For reasons that have to do with the conservation of energy, atoms have a tendency to try to saturate their outer shell of electrons. Typically, the first shell, the first layer of electrons around an atom, has 2 slots for electrons. When there is only 1 electron in this shell, like for hydrogen atoms that typically have 1 proton and 1 electron, the atom will be prone to look for an association with another atom that also misses 1 electron on its outer shell. This is why a very common form of hydrogen is not independent hydrogen atoms, but rather dihydrogen, a molecule with 2 atoms of hydrogen. The 2 atoms share their electrons, which gives the dihydrogen molecule 2 electrons on its single electronic shell, and that is a rather stable association. Now the first electronic shell has 2 slots, and the helium atoms happen to have 2 protons and 2 electrons. So the atom doesn't need any association with 1 or several others to complete its electrons count. This is the reason why helium is inert. It doesn't search to react with other elements, because in that respect it is self-sufficient. Now the first shell of electrons has 2 slots, but the following shells have more. They have 8. And this is why there are other elements that are in a similar situation as helium. The following one is neon, which has 10 as its atomic number. 10 because it has 10 protons and also 10 electrons that make it electrically neutral. This means its first electronic shell of 2 electrons and its second shell of 8 are both full. This is the reason why neon shares a lot of properties with helium. In particular, the same lack of interest for chemical reactions, the same inertness. And the following noble gases in the periodic table, the members of the same group, argon, krypton, xenon, have this same characteristic. Their outermost electronic shell is full. They are not inclined to react, except under extreme conditions that never happen on Earth in our direct environment. And this is why these gases are used in applications when no chemical reaction is wanted. For example, they can be used to create an atmosphere around very reactive material to prevent explosions or unwanted reactions. To mention just a well-known practical use of helium, of a noble gas that is not prone to reaction, I could mention the replacement of hydrogen by helium in Zeppelins after the Hindenburg disaster, the accidental explosion of the Hindenburg, a German Zeppelin filled with hydrogen, as it was landing in America in New Jersey after a crossing of the Atlantic in 1937. Hydrogen was cheap and efficient as a filler gas for balloons and zeppelins. But it is also highly flammable, and it was only a matter of time before an accident would happen. Helium is very safe in comparison. It cannot explode or burn. Replacing hydrogen with helium didn't save zeppelins that still disappeared because they were too slow and not very cost-effective compared with planes. But if one day zeppelins return, it could probably be with a non-reactive gas like helium. Now let's move on to element number 3, our first metal, lithium. Lithium has been under the spotlight in recent years because it has turned into a strategic resource with the rise in demand for rechargeable batteries, a crucial component for electric cars in particular. There are several technologies for these batteries, but the ones using lithium are the most effective right now. Lithium is highly reactive, and it is always found either associated in molecules with other elements, like dioxide, or in a solution in ocean water. But why is it so reactive? For the same reasons, helium is not reactive, basically. It's because of the electrons. Lithium has 3 protons, so it tends to bind 3 electrons with opposite electric charges. But we saw before, when I told you about helium and noble gases, that the outer layer of electrons was important for chemical reactions. Lithium has a first layer of 2 electrons, which is full, and on top of that, one lonely electron on the next layer, which could have up to 8. So this third electron is awkward. It can easily be lost, which turns the lithium atom into an ion, an electrically charged atom, because it lacks an electron. These lithium ions have a high solubility. They will mix easily with seawater, and this is why lithium can be found in seawater, but in very low concentration. To be exploitable in mining, it is found mainly in salt pans or salt flats, which are places where a salted water pool has evaporated, typically in deserts. The minerals found in these expanses of salt are much more concentrated than in ocean water, and from them lithium and other minerals can be extracted. This is why the biggest exploitable lithium deposits are in countries with large salt flats like Chile, Argentina, Bolivia, Australia. A general rule when it comes to the quantity of every element in the universe is that the simpler and lighter atoms are, the more there will be of them. We have seen before that hydrogen and helium accounted for most of the mass of atoms in the universe. But even though lithium is also a relatively light and simple element, with its 3 protons, it is not very frequent, and actually less so than the elements that follow it in the periodic table. This sounds odd or paradoxical, but it is because the nucleus of lithium tends to be unstable. It doesn't take much for it to break, to fission, and lose one of its protons, which transmutes it into helium. This is why it is an exception to the rule that lighter elements are more abundant. Lithium is relatively rare for such a simple element. And lithium is also the first element of a family that has similar properties like helium was with noble gases. This particular family is called alkali metals, and it includes lithium, sodium, potassium, and bigger and rarer atoms like rubidium, cesium, and francium. Alkali metals are at odds with noble gases in a sense. Noble gases are inert. Alkali metals are very reactive. And the reason for this property is this one extra electron that makes them very prone to chemical reactions. So typically, alkali metals are not found pure in nature. They are associated in molecules with other atoms due to past reactions with them. And when refined, a block of alkali metal needs to be kept in an inert liquid or an inert atmosphere, because just a contact with the air could provoke a chemical reaction, a combustion. Our next element is beryllium, with atomic number 4, and it is another light element that is rare. It appears mainly in the core of stars when they approach the end of their lives. And when they do, they begin to fuse bigger elements because their hydrogen reserves are depleted. But this beryllium disappears quickly because it fuses into even heavier elements. On Earth, beryllium is quite marginal in Earth's crust, but it can be found. For example, it's a bit anecdotal, but there is some in some gemstones like aquamarines or emeralds. You now understand how the electron shells work. So beryllium has a first complete shell of 2 electrons, and on its second shell it has 2 electrons out of a possible 8 for this shell to be full. This makes beryllium and other members of its family, which also have 2 spare electrons on their outermost layer, rather prone to chemical reactions too. And actually, in natural conditions, beryllium is not found alone. It is always in combination with other elements, forming different minerals. This family of elements, headed by beryllium, is called alkaline earth metals, and it includes other elements we will review later, like magnesium, calcium, strontium or radium. Element number 5 is boron, another relatively rare element, which has a few industrial uses. One of the uses of boron is as a neutron capturing agent, in the nuclear industry in particular. But what does it mean and how does it work? Until now, I told you essentially about protons in the nuclei of atoms. Protons which determine the nature of an element and its atomic number. But there is a second type of particles that can be found in the nuclei of atoms, neutrons. Neutrons are a lot like protons, but without an electric charge. And for a given element, the number of neutrons can vary. A different number of neutrons means that properties are going to be slightly different, starting with the mass. For the same number of atoms, there is more matter if there are more neutrons. So, depending on the elements, there can be many versions of the same element, each version with a different number of neutrons. These versions are called isotopes. Typically, an element can have different isotopes that are not very stable. They have too few or too many neutrons, which will make them decay or turn into another element. So many of these isotopes are unstable, short-lived. They won't last. But many elements have various naturally occurring isotopes that can be perfectly stable, or stable enough to last a long time before they eventually decay. Boron, for example, has 2 naturally occurring isotopes, one with 5 neutrons and one with 6. The one with 5 neutrons is called boron 10 because it has 10 particles in the nucleus, 5 protons, this is what makes it boron, and 5 neutrons. And the version, the isotope with 6 neutrons, is called boron 11, 5 protons and 6 neutrons. But in total, there are 13 isotopes of boron that have been discovered, ranging from boron 7 with only 2 neutrons to boron 21 with 16 neutrons. But contrary to 10 and 11, which are stable, all the other ones vanish quickly. Those with a mass below 10 tend to decay into helium, and those above 11 turn into carbon, the next element I will tell you about. Now, boron is useful as a neutron absorber in nuclear facilities because it easily captures neutrons, and free neutrons are what produces chain reactions of fission in a nuclear reactor or a nuclear explosion. Heavy atoms that are prone to fission capture these free neutrons. This makes them unstable. They fission into lighter atoms and also liberate more neutrons that are available for ever more reactions. This is the principle of a nuclear chain reaction. Boron is useful as a mean of control. Because it is neutron hungry, it will tend to stop or poison, as is often said, the free circulation of neutrons that provokes the chain reaction. So it is useful to pilot a nuclear reactor, or in case of an accident, to capture and neutralize the flow of neutrons and stop fission reactions from happening. Now let's move on to a very important element, without which organic life as we know it would be impossible: carbon. Carbon has atomic number 6. It has 6 protons, and it is estimated to be the 4th most abundant element in the universe, after hydrogen, helium, and oxygen. In the Earth's crust, it is the 15th most abundant, but in our bodies it is the 2nd by mass after oxygen. Our bodies are made of 18 to 19% carbon. What distinguishes carbon from other elements is the number of shapes and compounds it can be found in. First, because carbon atoms can bond together in very diverse ways. As you know, diamond is pure carbon, and it is the hardest natural material we know of. But graphite, which is used in pencils, and that is soft enough to be used to write, is also pure carbon. The only difference between the two is how carbon atoms are arranged between them. There are other forms. Carbon can be shaped naturally or artificially into nanotubes or different kinds of mesh. These different arrangements are called allotropes. All elements can have different states. They can be liquid or solid or gas. Allotropes are something else. They are different arrangements of atoms. Atoms can be bonded together in different ways. So diamond and graphite are 2 allotropes of carbon. They both are made of carbon in a solid state, but they are different arrangements. The different structure of carbon atoms gives them very different properties. Apart from its allotropes, another remarkable property of carbon is its unique availability for the formation of chemical compounds under standard conditions. With its 6 electrons, 2 on the first shell and 4 on the second one, it has the capacity to form up to 4 bonds with other atoms. This property, plus its relative abundance, has led to a huge number of compounds with carbon existing. more than 200 million have been described and indexed. There are rather basic molecules and compounds like carbon dioxide, one carbon atom with two of oxygen, carbon monoxide, or all the hydrocarbons, which, as their name says, are compounds of hydrogen and carbon. But this is just the tip of the iceberg. There are also countless polymers, very big and complex molecules, in which carbon, oxygen, and hydrogen are abundant. All biological life forms we know of rely on carbon chemistry. And this is why even astrobiologists, people who study the possibility of life in other places than Earth, how it could appear, be disseminated, evolve. So astrobiologists generally believe that carbon would also be crucial to extraterrestrial life forms. Not out of a lack of imagination, but because of the chemical properties of carbon, this property to bind with many other elements in many different ways, and be used to build bodies as well as transport energy. Maybe a life form without carbon is possible, but it looks so much more likely to include carbon, and this comes down to the properties of this element that are determined by its atomic structure once again, and on top of that, its availability. As we said, it is the fourth most abundant in the universe. After carbon, we have nitrogen, which is number 7. Nitrogen is another abundant element on Earth, and the proof is that you are currently immersed in it. Almost 80% of the air we breathe is nitrogen. So, under standard conditions, nitrogen is a colorless and odorless gas. After oxygen, carbon, and hydrogen, nitrogen is the fourth most abundant element in our bodies. It makes about 3% of them. It is present in particular in amino acids, big compounds that are incorporated into proteins. Nitrogen is also vital to plants, and you find some in nitrates and ammonia. Nitrates are compounds that nitrogen forms with oxygen, and ammonia with hydrogen. Both are important fertilizers for plants. We are reaching number 8, oxygen, which, as you know, is another crucial ingredient of life. There is oxygen in the air, about 20%, in our bodies, and also in the ground. It would be easy to think of oxygen just as a gas, because we breathe some. In reality, oxygen also forms oxides with many other elements. So much so that about half the Earth's crust consists of oxygen by mass. Pure oxygen under atmospheric conditions is a gas, and atoms tend to bind 2 by 2 to form dioxygen, O2. Oxygen can also give water combined with hydrogen and all sorts of oxides, with iron, sulfur, carbon, and in particular in the Earth's crust with silicon. Obviously, we need oxygen to breathe. What we call breathing is ultimately a chemical reaction. oxygen reacts with molecules derived from food. This produces energy that we use, and a main waste product, which is carbon dioxide, which we expel. To continually extract this energy from organic molecules, living beings need to breathe continuously or almost continuously. We need a constant supply of oxygen, and this is what our lungs provide to our bodies. I told you that when it is pure, oxygen comes in pairs of oxygen atoms, dioxygen, or O2. But oxygen also has another form in the atmosphere, with 3 atoms, O3, which is also known as ozone. Ozone is an allotrope of oxygen. You remember what allotropes are? A different form taken by an element under the same conditions, a different arrangement of atoms. Under the form of ozone, oxygen also protects life on Earth, because ozone has a strong capacity to absorb ultraviolet radiation. I already told you a lot about oxygen in previous stories. So for now, let's move on to our next element, number 9, fluorine. As all the elements I have told you about until now, fluorine is the first of its group, and the group it heads is called halogens. Apart from fluorine, halogens include chlorine, bromine, iodine, and other bigger atoms. These elements, these atoms, have 7 electrons on their outermost electronic shell, 7 out of 8 possible slots, and this makes them highly reactive. They really want to attract another electron. Like lithium, we saw earlier, really wants to give up its 3rd electron. So fluorine tends to react with all other elements except noble gases like helium or neon that are inert. Under standard conditions, fluorine is a gas that is highly toxic. It is toxic due to its reactivity. When it comes into contact with moisture, with water, it combines with oxygen and hydrogen. The compound it makes with hydrogen is a powerful acid. It also reacts with the skin, producing burns that could even turn to frostbites if fluorine is liquid. But don't worry too much about it. Only a bad manipulation of chemicals could make you breathe fluorine, because it cannot stay long as a gas in the atmosphere, since it reacts immediately with anything. There is a good amount of fluorine on Earth. It is number 13 among elements in terms of terrestrial abundance, but it is found as a mineral in combination with other elements like fluorite with a T, which is the association of fluorine with calcium. We are reaching element number 10, neon, and with it we are completing a little cycle. Because you remember that neon is the 2nd noble gas, the one that comes after helium in the noble gases family. Its outermost electronic shell is full with 8 electrons, so like helium, Neon is uninterested in reacting with other elements. Neon is a good example of how elements are not evenly distributed in the solar system or in the galaxy. Neon is actually very common in the universe. It comes fifth in abundance after hydrogen, helium, oxygen, and carbon. But on Earth, there's barely any of it. It is found only as traces in the air. So how is it that there is so little on Earth? This is so because neon is very volatile, and it forms no compounds that would fix it to solids like nitrogen or oxygen. So it is believed that almost all neon in the early solar system escaped from the protoplanets that formed near the Sun under the warmth of this new star, including all the rocky planets from Mercury to Mars, which includes Earth. This neon went far to the periphery, beyond Jupiter, where it is rather common, rather abundant, whereas we only have traces of neon on Earth. One use of neon is for lighting. You know about neon signs that were popular in the 20th century as commercial signs. They tend to disappear and be replaced with LEDs that imitate them. But neon signs use neon and electricity to produce light. Inside a neon tube or a neon lamp, neon and other gases are imprisoned at a low pressure and with two electrodes. When sufficient current is supplied between the electrodes, the gas produces a luminous glow, and this is how neon lamps or tubes work. Element number 11 is sodium, the second alkali metal after lithium, and another rather common element on Earth, the sixth most abundant. You remember lithium was very reactive with its single electron on its outer shell of electrons. And sodium has the same characteristic. A first shell, a first layer with 2 electrons, which is full, another one with 8 electrons, which is also full, and one single electron on the third, which can easily be given away by the sodium atom. So sodium is not found pure, but combined with other elements, often under the form of salt. But what is a salt, by the way? There is a common usage meaning of salt, as in table salt, the mineral that can be added to our food. This table salt is sodium chloride, a compound made of the same number of atoms of sodium and chloride. This type of compound is called Ionic compound, and it could easily be confused with a molecule, but it is not really one. A molecule is an association, a group, between atoms that share their electrons. These atoms are chemically bound. An ionic compound is something else. It is held together by electrostatic forces. In other terms, it is a compound of ions. Ions are atoms or molecules that have a difference between their number of protons and electrons, which makes them electrically charged, positively or negatively. For example, In the case of sodium chloride, table salt, we have atoms of sodium with their 11th electron that could easily be given away, and we have the same number of atoms of chloride with 17 electrons. They just miss one to complete their outer shell. So chlorine atoms will steal one electron from sodium atoms, making them negatively charged, whereas sodium atoms with one missing electron become positively charged. And these two types of ions attract each other because of their opposite electric charges. As they come together, they create a well-organized structure, a crystalline structure, in which all the ions replicate the same arrangement. It is orderly. And electrostatic forces, in this case also called ionic bonding, keeps the structure together. So these are not molecules. Actually, an ionic compound can be made of atoms that have opposite charges or of molecules that have opposite electric charges too, and adopt this structure. In chemistry, a salt is any chemical compound made of ions, positively and negatively charged. As a result of their opposite charges, it has no net electrical charge. Positive and negative ions cancel each other. So table salt is a salt in chemical terms, but there are many more possible chemical salts. Let's advance to element 12, magnesium, the second alkaline earth metal after beryllium. I told you earlier that beryllium was rare in the universe and on Earth because it got quickly depleted after its formation in stars. Magnesium doesn't have the same problem. It is produced in large aging stars when they have consumed a big part of their hydrogen reserves and they start to fuse heavier nuclei. In such stars, the addition of 3 helium nuclei to 1 carbon nucleus gives a nucleus with 12 protons, 3 times 2 from helium atoms and 6 with carbon. And we get a new magnesium nucleus. This happens by the end of the life cycle of large stars that end in a supernova, which expels all this new magnesium into the interstellar medium, where it can serve, it can be recycled into a new star system. So, like for all other heavier elements, from beryllium with atomic number 4 to the heaviest elements on the periodic table, the magnesium atoms we have on Earth didn't form at the start of our universe's expansion with the Big Bang. They formed later, a few billion years later probably, in stars that died and whose material was recycled to form the solar system. Magnesium is a metal, but the term metal is a bit like salt. Its definition may depend on the context. So, what is a metal exactly? Here again there is the everyday common definition. What we call metal is any material that conducts electricity and heat, that shows a lustrous appearance when it is polished or broken, and generally metals are relatively heavy compared with other materials. So we kind of know, intuitively, what is metal and what is not in our daily lives. Most of the time we expect to find metals in a solid state at room temperature. But we also know that there are exceptions to this. For example, mercury is liquid, and sometimes we use metal objects like aluminium ladders that are surprisingly light, but aluminium is a metal. Physics and chemistry need more precise definition. In physics, a metal is any substance, not necessarily an element. It can be a combination of elements, like an alloy, any material or substance that is capable of conducting electricity when there is no heat at all, at absolute zero. And this definition can give counterintuitive results. All current metals, iron, copper, gold, etc., remain metals under this definition. But in some conditions, with the right pressure, plenty of elements can become metallic. For example, hydrogen. Inside big gas planets like Jupiter or Saturn, it is believed that hydrogen in the deeper layers of this planet is pressurized enough to become metallic, meaning essentially that it can conduct electricity. Sodium is regarded as a metal, but it can lose its metallic property if exposed to extreme pressures above 2 million times atmospheric pressure. In that case, it ceases to conduct electricity. But at even higher pressures, it is theorized that it should get it back and become a metal again. So, based on this definition, metal or metallic is as much a state, a property of a material in certain conditions as it is a characteristic. This tends to blur the frontier between metals and non-metals. And then there is yet another definition, which is the one from astrophysics. The term metal in astrophysics is cast more widely to refer to all elements in a star that are heavier than helium. That is to say, basically all elements except hydrogen and helium. This definition contradicts the common definitions of chemistry and physics. In astrophysics, elements like carbon, oxygen, or nitrogen become metals, which they are not in chemistry. So, as you understand, it depends on the definition. The one from astrophysics is probably too broad for other disciplines. It makes sense in astronomy because it's about the genesis of elements in stars. But whatever definition of metal we choose, magnesium falls into this category. It conducts electricity at standard conditions and also at absolute zero. Another aspect of magnesium is its importance for life. Alongside the elements that really form the main building materials of our bodies, oxygen, carbon, hydrogen, magnesium is one of the many elements that are present in small quantities but are essential to life. It is in every cell and in hundreds of enzymes. Enzymes are big proteins that act as catalysts to chemical reactions in our bodies. We absolutely need them to ensure our metabolism works correctly. And these enzymes require magnesium ions to function. For plants, magnesium is necessary to synthesize chlorophyll, which is essential to photosynthesis. So here again, an essential element to life as we know it. We are all rather familiar with aluminium because it is quite present in our daily lives, in plenty of appliances, in cars, in metal cans for drinks. And you may have noticed that it is also very lightweight for a metal. It is not very dense, and we will see why. In the previous story, I told you about families or groups of elements that are presented vertically in the periodic table of elements. And the elements within these groups share some of their properties. When it comes to their propensity to associate with other elements, to form molecules and compounds, these properties are strongly determined by their number of electrons. When they associate with others, atoms try to fill, to saturate their outermost layer of electrons. And this makes them strongly inclined to look for the few ones they miss, or to give away one or two. And it makes them prone to react more or less with other elements. Elements of the same group, of the same family, have the same number of electrons to give away or to find. And this is why they share some of their properties with others from the same family. Aluminium is in the family of boron that I told you about already. And this boron family forms compounds primarily with oxygen. It bonds very easily with it. This is the reason why, on Earth, aluminium is almost never found in nature as a free element. It almost always comes as an oxide in association with oxygen. So there's a lot of aluminium in the Earth's crust. It is even the third most abundant element there, after oxygen and silicon. But it almost always comes associated, not alone. In particular, in a type of rock called bauxite. Bauxite is a kind of sedimentary rock that is often reddish-brown, but it can also be white. And the composition of this rock can vary, but it is rich in aluminium. It contains different types of aluminium oxides. Typically, the way to extract metals is to mine ore, for example iron or copper ore being a general term for compounds that are rich in one or several metals. Because in nature, metals are almost never found pure and alone, separated from other elements. For most common metals, this ore is smelted inside a furnace immediately after extraction, if it is rich enough, or, if it isn't, after a first treatment. And along this processing, unwanted elements are eliminated like this. They are separated from the metal that comes out pure or almost pure from the whole process. In the case of aluminium, things are a bit different. The ore is bauxite, and it is not smelted, but rather treated chemically and electrically. First, aluminium oxides are extracted because bauxite contains other elements that are unwanted. This gives alumina, which is pure aluminium oxide. And this alumina is treated electrically. It consists of aluminium plus oxygen, so the goal is to separate these two elements and collect only pure aluminium. This is achieved with electrolysis, the separation of elements using an electric current between two electrodes. In the case of aluminium electrolysis, one electrode is made of carbon that serves as an alternative pairing to oxygen atoms. After they separate from aluminium, they bond with carbon to make carbon monoxide or carbon dioxide. This gets rid of oxygen, and pure aluminium can be harvested, collected this way. Aluminium has different things, different aspects that make it appealing. It is relatively easy to work with. The abundance of bauxite makes it accessible. It is not a rare element. I told you before that it is the third most abundant in the Earth's crust. And it is also lightweight for such a strong material. So, aluminium has appeal, and indeed it has many uses, but it can be relatively expensive to produce, because it requires a lot of electricity. Really a lot. An aluminium plant can consume as much electricity as a small city. And this is why, traditionally, since this production process was discovered and industrialized in the 19th century, aluminium plants have been built near cheap electricity sources, like dams that produce hydroelectric power. And the production of aluminium also has a significant environmental cost because of the energy required first, and also because of the release of carbon dioxide as a byproduct. But still, aluminium is very useful when strength and lightness are required. For example, to make aircraft. Since the rise of modern aviation, planes have been using a lot of aluminium parts. It is also used for packaging, for example, to can beer or sodas. But why is aluminium so light in comparison with other metals like iron? There is not one, but rather two reasons to it. The molecular mass and how atoms are arranged. So, first, the molecular mass. A nucleus of aluminium always has 13 protons, and the most common isotope of aluminium has 14 neutrons, so that makes 27 particles in the nucleus. Iron typically has 56 particles in its nucleus, so it has twice the mass of aluminium for one atom. And on top of that, the way aluminium atoms are arranged at atmospheric conditions on Earth leaves more void between them, more space. So it takes 1.5 times more iron atoms to fill the same volume. And between the lower molecular mass and less atoms, these are the reasons why aluminium objects like aluminium ladders or cans feel so lightweight in comparison with iron or steel. They require less atoms, and on top of that, these atoms have half the mass. In total, the density of aluminium is about 1/3 of the density of iron. Our next element is another one that is very present in our daily lives. It is silicon, number 14. I told you before that silicon was the second most abundant element in the Earth's crust, after oxygen. Silicon alone represents 28% of the mass of the Earth's crust. And in association with oxygen, it forms compounds that are called silicates, which are also commonly called rocks. These minerals, silicates, represent 90% of the Earth's crust, and under the same forms associated with oxygen, silicon is widely distributed in the universe, in cosmic dust, asteroids, and rocky planets or satellites. It is the 8th most abundant element in the universe. And I told you that silicon was extremely present in our lives, and this from prehistoric times. Many building materials or materials for craft contain some: clays, sand, stone. Since it is a major component of sand and rock, it also ends up in cement, in concrete, so we find it in our houses or our roads. Glass is also made primarily from silicon. There are different possible compositions for glasses, because glass is the name given to a type of solid that is often transparent and chemically amorphous. Amorphous in chemistry. This means that if you look at it even at a microscopic scale, the atoms it is made of are not ordered, they are not arranged following a pattern, but instead they form a pile arranged randomly. Hence the term amorphous, that suggests that there is no shape, no pattern to it. So in chemistry, an amorphous solid is the opposite to a crystal. A crystalline structure is one where there is a periodic arrangement of atoms that repeats itself, the exact opposite to an amorphous structure. That can be a bit confusing because in everyday language, glass and crystal are sometimes considered almost the same thing, and they can look the same, but if we look more closely at their structure, they are very different. Yet another frequent use of silicon is in silicones, which are very large molecules, and there are different sorts of silicones with different properties. But what they have in common is that they contain a lot of silicon atoms, together with other elements we already reviewed, like oxygen, carbon, and hydrogen. Silicones are used in a lot of things, in sealants, in lubricants, adhesives, for insulation, in cookware. Yet another critical use of silicon is in electronics. Highly purified elemental silicon is essential to making the transistors and chips that are used in electronic devices. So computers, smartphones, all the onboard electronics in cars, in home appliances, all of this could not function without silicon. The property of silicon used in these applications is that it is a semiconductor, which, as the name says, means that it can conduct electricity, but not always or not perfectly. A semiconductor falls somewhere between an insulator, for example glass, we just talked about it, and a conductor, such as iron or copper. Silicon is also an important element in biology. Not that much for large animals, only traces are present in our organisms, but it is present and necessary in small quantities in many plant tissues. And there are also different microorganisms, microscopic algae and animals, that use it to build a kind of tiny skeleton for themselves. Element number 15 is phosphorus, yet another critical element to life. When I told you of nitrogen in the previous part, I explained that nitrates were important for plant growth and used in fertilizers. So are phosphates, that are different compounds that contain phosphorus. Phosphorus is not a very rare element. In 1 kilogram of earth crust, there is about 1 gram, 1,000th of phosphorus. But it is very reactive in normal conditions, and this is why it is never found as a pure element on Earth, a free element. Pure phosphorus at normal conditions can have different forms, different allotropes. You remember that an allotrope is a different arrangement of the same atom that can give the element a different appearance and properties. For example, graphite, also known as pencil lead, is chemically identical to diamond. Both are pure carbon, but the atoms are arranged differently. And here, pure elemental phosphorus comes under two major forms, two allotropes, white and red phosphorus. You know the term phosphorescence, which is used for things that glow after illumination. It actually comes from phosphorus, because it was observed that white phosphorus had like a faint glow when exposed to oxygen. This glow is produced by oxidation of phosphorus when it has its white form. It doesn't happen with red phosphorus. The correct term to refer to this phenomenon should be chemiluminescence. Nowadays, the term phosphorescence names another process that is independent, unrelated to phosphorus. It's a bit confusing. But this term, phosphorescence, historically appeared because of the glow of white phosphorus. Our next element, number 16, is sulfur. Under normal conditions, sulfur is solid and looks like yellow crystals. A particularity is that sulfur atoms tend to go by 8 in these normal conditions, and they form molecules with 8 atoms. Sulfur was one of the first elements to be identified because it is relatively abundant. It was known in ancient times from China to the Mediterranean. Nowadays, a lot of sulfur is obtained from the treatment of oil and natural gas. When they are refined, stripped of their unwanted components, elemental sulfur is a frequent byproduct, trash, of refining. And this covers the needs of the chemical industry that uses sulfur for fertilizers to make matches or insecticides. After the elements that make the basic bricks of organic life, like oxygen, hydrogen, carbon, that are present in large quantities in our bodies, sulfur is another essential element to life. It is present in compounds that make amino acids, proteins, in vitamins, or in keratin, that is the building material of our hair or nails. Many elements are necessary to organic life, actually. Apart from very rare and heavy atoms that we will review later, we need dozens of different elements, many of them just as traces. One of the few exceptions among those we have just reviewed is aluminium. It is not part of the biochemical functioning of any living being that we know of. After sulfur comes chlorine with number 17. Under normal conditions, chlorine is a pale yellow or greenish gas, but it is extremely reactive, which is what makes it toxic when it is a gas, but also explains why it is absent from the air. It reacted long ago with oxygen, nitrogen, or sodium to form compounds like table salt, which I told you about when we discussed sodium. In antiquity and the medieval period, salts containing chlorine were quite popular with alchemists, because by heating and mixing them, they could make spectacular experiments. For example, they could make a substance called aqua regia, Latin for royal or regal water. Aqua regia was a mixture of nitric and hydrochloric acids. First, it is a fuming liquid, so it makes an impression, but it also has the power to dissolve gold, which gave it an aura of magic. By the way, since we are in the Middle Ages, when were all these different elements we are talking about discovered? The way elements are classified changed a lot in the past 2 or 3 centuries. There were many different models that arose from the late 18th century to the 20th century. Prior to that, the nature of matter was the subject of much speculation, from the ancient world to the Middle Ages. A common model was the belief that matter was made of a small number of basic elements: water, fire, air, earth. In some cultures, they also included metal or wood. This conception was sidelined in modern times, when the first chemical elements were discovered. We know today what water, air, or fire are made of. They are not essential basic elements, but instead they are made of different atomic elements. Water is oxygen and hydrogen. Fire, if we just consider the flame, is primarily a mix of carbon dioxide, water vapor, oxygen and nitrogen, plus whatever elements the burning object may contain and release. Air, if we take the air around us, is a lot of nitrogen and oxygen, plus a bit of hydrogen because there is moisture in it, carbon, and traces of plenty of other gases. Earth, as we have seen, is going to vary a lot depending on where you take it, but it contains always about 2/3 of oxygen and silicon, plus plenty of other elements. It can contain a lot of water too, if it is wet. So all these primordial elements that were thought to be the basic components, the basic bricks of matter in ancient times, are in reality compounds of other elements. The atomic classification is something that arose from the late 18th century and during the 19th century. The first periodic table of the elements as we know it was from 1913. At the time, it had a few dozen elements, way less than today. Today there are 118, because some of them had not been discovered yet. If we look at the timeline of the discovery of elements, out of these 118, only 14 were known in antiquity. These included a lot of metals: iron, obviously, copper, zinc, silver, gold, platinum, tin, lead. We will go through many of these metals later. 27 more elements were discovered from the Renaissance to the Age of Enlightenment, 3 centuries between the 16th and the 18th centuries. That could be called the time of the scientific revolution. Most of the elements I told you about until this point are among them, with the exception of noble gases like helium or neon that were discovered in the 19th century, and lithium too. The 19th century was like a golden age for chemistry. It started with 41 elements already known, and 42 more were identified during this century. It was also the time when the atomic theory replaced older approaches, and the systematic classifications of atoms appeared. This good period for discoveries in chemistry continued in the first half of the 20th century, which is when 14 more elements were named, including plenty of naturally radioactive elements like plutonium or francium. One thing that had changed by the beginning of the 20th century was the approach to searching for new elements, waiting to be discovered. The fact that the number of protons in the nucleus was the factor that made an element what it was meant that there could only be one element with a given number of protons, one element with 1 proton, one with 2, one with 3, and so on. So, as the periodic table was completed, chemists and physicists now looked for the element that had a given number of protons. And sometimes these new elements could be synthesized artificially. Some have been created that do not occur naturally. Among very big atoms with dozens of protons and neutrons that are often unstable. I will elaborate a bit more on these very big giant atoms as we approach the end of the periodic table. But some of them only exist or have existed in labs. And it's always interesting to know they are real and that they can exist, but they are not used for anything and cannot be found in nature. They have names most of us never hear of, like oganesson, tennessine, or livermorium. And they were synthesized in the past 20 years by making atoms collide in colliders or by bombardments with particles. So let's move on to number 18, argon. Argon is the third noble gas after helium and neon that we already covered. The name argon is derived from Greek and it means lazy or idle, which is not surprising for a noble gas, as the other members of this group, and for the same reasons, it has a very low reactivity. Argon is used for fluorescent lighting like neon, and also due to its low reactivity, it is used in high-temperature industrial processes as a shielding gas or for welding. When temperature rises, a lot of elements become more reactive. They are excited by this available caloric energy around them. So this is when a noble gas comes handy. For example, an argon atmosphere is used in graphite electric furnaces to prevent the graphite from burning, which would happen if it was surrounded with a normal oxygen-rich atmosphere. Number 19 is potassium, the third alkali metal after lithium and sodium. Chemically and visually, potassium is a lot like sodium. In normal conditions, it is a white metal or silver-like metal that is very soft. It could be cut with a knife, and it is very reactive. It reacts immediately with oxygen in the air. So, as you now understand perfectly, this means it's not going to be found free, pure, in our environment, but rather in minerals or dissolved in seawater. An essential role of potassium in our bodies is for nerve transmission. Nerve transmission needs potassium ions, that is to say, potassium atoms stripped of electrons with an electric charge. These particular ions can cross nerve cell membranes, and this is why we absolutely need some potassium in our food. Fresh fruit and vegetables provide some, and the name potassium actually reflects how it was traditionally obtained. It comes from potash, which are salts containing potassium that were produced by taking ashes of plants, adding water, heating, and evaporating this solution. Potash had different uses long before the Industrial Revolution. In ancient times, it already served to make soap or glass, in ceramic, or for bleaching textiles. It is an additive that has been in use for thousands of years. Element number 20 is calcium, another abundant element on Earth that we encounter generally as calcium carbonate, associated with carbon and oxygen. It is found in eggshells, in the shells of gastropods, in pearls, but there are huge deposits of calcium carbonate in geological layers, made of the skeletons of ancient sea life forms, especially from plankton. For millions and millions of years, the microscopic skeletons they made using calcium have accumulated at the bottom of the oceans. They have been compressed, and in different places, like in Western Europe, these layers of sediments, have then emerged. This is what chalk is made of, calcium carbonate. As you know, calcium is also a vital element for our bodies. It is known to serve for bones, but it goes beyond this role. It is actually the fifth most present element in the human body, and it plays a role in the health of our muscular, digestive, and circulatory systems. It serves in the synthesis and the operation of blood cells. We couldn't live without it. Now that we have passed element 20, we're going to start to encounter less ordinary and more mysterious elements. We still have a lot of well-known metals to talk about, from iron to copper or gold, and some of them are rather abundant. But we will also encounter other elements we rarely even hear about, like element 21, called scandium. Scandium is part of a set of 17 elements that are often called rare earth metals or rare earths. Each of them has a few industrial applications, generally very specific, as additives in alloys, for components in electronics, or as agents in industrial processes, catalysts. You probably never heard their names unless you have a job that justifies it. Apart from scandium, which is element 21, these rare earths include number 39, yttrium, number 57, lanthanum, 58, cerium. Actually, all elements from 57 to 71 are part of this group. These different elements are found in association between them and with other elements, other metals. So refining of rare earth deposits are always compulsory to extract them and get them in pure form. Demand for some of these rare earth metals has skyrocketed in recent years due to different applications in electronics like LED lamps, screens, electric vehicles. And at this point, China is by far the most important supplier in the world. So there is a scramble around the world at the moment to put in production other rare earth mines or sites, because these are strategic resources that could also potentially become very lucrative in the next decades. Element 22 is titanium, a metal that is only found as an oxide in nature, but can be purified, reduced, to produce an element that has a silver color, a relatively low density, it feels lightweight, but high strength and high resistance to corrosion. Strength is what titanium is known for. When it is pure, it is as strong as steel, but less dense. Most of the time it is used in alloys with iron and aluminium, when high-performance materials are required, for example for aerospace. It also serves as a catalyst. Titanium is denser than aluminium, about 60% denser, but more than twice as strong. So looking at the ratio of its strength to its weight, it is a great choice as a high-performance material. And in various applications, a more upscale alternative to aluminium. Number 23 is vanadium, another metal that was found out in the 19th century, and also presents this silvery grey aspect. It is mainly used in the production of steel and aluminium alloys. It was discovered at the beginning of the 20th century that a small amount of vanadium added in steel could considerably increase its strength. So since then, many steel objects that need to be particularly strong, like gears, some bicycle frames, crankshafts in engines, these can be made of steel containing vanadium. Another element often added to steel is element number 24, chromium. You know about stainless steel, also called inox. This type or this family of alloys was invented when it was discovered that an amount of chromium, typically 10% or more, could make steel resistant to corrosion. It no longer rusts. Chromium forms a coating, a passive film, that prevents damage to the metal. So chromium is very resistant to corrosion and also a hard metal by itself. Apart from stainless steel, another use is chrome plating, the creation of a thin film, a thin layer of chromium on metallic objects. You've seen the shiny parts of motorbikes or some cars. These are chrome-plated because chromium is also very resistant to tarnishing. What we call tarnish on metals is in fact just a thin layer of corrosion that appears on them due to a reaction of oxidation with oxygen in the air. It is not always oxygen, actually. For example, silver tarnishes in contact with air, mainly due to hydrogen sulfide, which is a gas present in traces in the ambient atmosphere. So chromium does not tarnish, and it can be highly and durably polished thanks to this, which is why it is used mainly as a mean to protect and embellish other metal parts. Element number 25 is manganese, yet another metal that serves in alloys. It often enters the composition of stainless steel too, because it improves strength and resistance to wear. It looks a lot like our next element, which is a big one, iron, number 26. Iron is a big deal. First, because it is, by mass, the most common element on Earth, just ahead of oxygen. There are more oxygen atoms, but an iron atom is about 3 times as heavy, as massive, as an oxygen atom. So, by mass, an estimated 32% of Earth is iron, and oxygen represents 30%, a bit less. Most of it is in Earth's outer and inner core, and the prevalence of iron in the crust is less. It is only the 4th element in the crust. It is believed a large part of this iron in the crust arrived in the late stages of Earth formation. Iron is heavier than other elements that make the bulk of the planet's composition. So, over millions of years, it tended to migrate towards the center of the planet, towards its core, which is believed to be very rich in iron. This didn't leave much of it in the outer layers of the planet, the ones that cooled down to form the crust. But during millions of years, as the planet had already begun to cool down and form a crust, there was an intense bombardment of meteorites. These meteorites are thought to have brought a substantial quantity of the water that we have on Earth, and also iron that stayed trapped close to the surface, close enough to be accessible today. Iron was, and still is, by far the most abundant metal in the Earth's crust. But it was not the first to be discovered and used by men. Probably because it is harder to work with than copper. The first metals used for tools and weapons or crafts were copper alloys like bronze, which is copper plus tin, or brass, which is copper and zinc. Hence the name Bronze Age. Bronze is an alloy and not an element. And actually the term bronze is a bit imprecise. It can be used for any alloy that has copper in it, and to a lesser extent tin. But why was copper used long before iron? Because extracting usable metal from iron ore requires furnaces that reach at least 1500 degrees Celsius, or 2700 degrees Fahrenheit. This is 500 degrees Celsius, or 900 degrees Fahrenheit, higher than required to smelt copper. That's a huge difference, hundreds of degrees, and this technical barrier to the use of iron is why the Bronze Age lasted for centuries, even thousands of years, before bronze was displaced by iron. By the end of the second millennium BC in Eurasia, and later in other parts of the world. The importance of iron since then has never decreased, and iron is by far the most common metal in our daily lives, in building materials, almost all appliances, tools, cutlery, cars. Under the form of steel, in particular, it is everywhere. Iron is also the cheapest of all metals due to its abundance and the size of the iron and steel industry. It costs only a few dollars per kilogram or per pound, which makes it cheaper than many foods by weight. And that's a huge contrast with pre-industrial times, when it was not a very precious material, but it was rare and costly enough for people to really take care of whatever iron objects they had. In the previous story, I told you that the very first elements, apart from hydrogen, helium and lithium with 1 to 3 protons respectively, appeared in stars as products of fusion between hydrogen nuclei. Elements 4 and 5, beryllium and boron, are a bit particular because they don't really form by fusion of nuclei. They would not remain stable, but they rather appear by a bombardment of existing nuclei by free protons. And there is relatively few of these two elements for that reason. They are not produced on a large scale. But if we leave them aside, after that, elements 6, which is carbon, to 26, iron, are fused by stars when they approach death. They have exhausted their hydrogen and helium resources, and they fuse heavier atoms in the last years or the last moments of their life, when they are approaching their final burst in a supernova. But all fusions are not exactly the same. I told you about that in more detail in previous stories about nuclear fusion and astrophysics. The fusions that give atoms up to 26 protons, up to iron, liberate energy when they happen. They are called exothermic. The energy needed to keep the new atom together is less than the energy needed to keep its predecessors together. In other terms, it needs less binding energy. So when the nuclei fuse, this excess energy is liberated, it is released. But above 26 protons in the nucleus, fusion reactions become endothermic. They need to absorb, to consume energy that is turned into binding energy. so no star could ever live durably on this fusion of these heavier atoms. Their creation, their appearance, happens only in the very last moments of a star's life, when considerable energy is released at once and can be absorbed to fuse these heavy elements. So, iron is the last exothermic element from the periodic table when it is created. The general rule is that the heavier, the more particles an atom contains, the rarer it is going to be. And as a broad general rule, it works. As we saw, there is incomparably more hydrogen and helium atoms, the first two elements, than any other in the universe, as far as we know. But the decrease in occurrence of the elements with their mass is not perfectly linear, not perfectly regular. I told you before that light elements like lithium or boron were relatively rare despite their small atomic number. This is because of their instability or the way they can be created. The abundance of an element also depends on its binding energy, the quantity of energy it would take to make its nucleus break apart and become atoms of a different element, or an isotope of the same element if it gains or loses neutrons. Iron and its various isotopes have one interesting characteristic here. They have the largest binding energy out of the thousands of different isotopes we know of. Thousands of isotopes because there are 118 elements, as I told you, and each of them has different isotopes, observed or theoretical. So that makes thousands of possible combinations. Out of all of them, iron atoms have the largest binding energy, which we could translate by saying that iron nuclei really prefer to stay the way they are. They are not inclined at all to break apart. This is thought to be a big reason behind the abundance of iron in the universe, despite its atomic number of 26. It is not such a light element, but once iron appears, it really doesn't go away easily. Iron nuclei will not get broken easily, nor participate in the fusion reactions of heavier elements. And this means that over time, iron tends to accumulate in the universe. Its share of total matter increases. Number 27 is cobalt, a metal that was discovered in the 18th century. Little trivia about cobalt. The name cobalt came from German kobold, which means goblin, the little fantasy creatures. But why call it goblin? Because ore containing cobalt seemed rather useless and toxic to the miners. It was poor in known metals that could be exploited, and when smelted, it produced fumes that contained arsenic, another element we will talk about later. These fumes were very toxic. But in 1735, these cobalt ores were found to be reducible to a new metal previously unknown, and it was named after this kobold word. Cobalt was the first metal discovered since ancient times, in more than 2000 years. Nowadays, cobalt is essentially obtained as a byproduct of the mining of more important metals like copper. But it has several uses in industry, for alloys in particular, and one that is very old, dating from before it was identified as an element. cobalt in compounds like cobalt silicate or cobalt aluminate gives a deep blue color to paints, to glass or to ceramics. And these cobalt blue pigments have been used since antiquity for paintings or jewelry or glass. In biology, cobalt is also an important component of vitamin B12, which is essential to all animals for the metabolism of cells and DNA synthesis. Let's continue with element 28, nickel. I told you before that a large part of the iron in the Earth's crust is thought to have come from meteorites by the end of the Earth formation process, when it was bombarded. The same applies to nickel, and this meteoric nickel is found in combination with iron. The main use of nickel is in metal alloys to improve their resistance to corrosion, or in plating for the same reason. Nickel is widely used to make coins, for example. One particularity of nickel is that it is one of only 4 elements to be ferromagnetic at room temperature. The other 3 are iron, cobalt, and a rare element called gadolinium, one of these rare earth elements we talked about before. Ferromagnetic means that they can be attracted by magnets. We are going to conclude for tonight with element number 29, copper, another major metal and probably the most significant industrially after iron. Copper is a rather soft and malleable metal which has a very high thermal and electrical conductivity at room temperature. So it is the material of choice for all electric cables, or more anecdotically for cookware, because heat will quickly spread out in a copper pan or pot. It melts at 1000 degrees Celsius, a significantly lower temperature than iron. And another thing that made its use easier by our ancestors during prehistory is that it can sometimes be found in a directly usable metallic form, what is called a native metal, one that is found free and immediately usable, as opposed to mixed with other elements in an ore. But the bulk of copper on Earth is in copper ore, and it was also the first metal to be smelted from ores around 5000 BC, thousands of years before iron. But because of its softness, pure copper is not very useful for tools or weapons. The first metals that were practically used on a large scale were bronze, that is to say, alloys of copper and tin. Copper in the Roman era was mined in particular on the island of Cyprus, and this is where the name copper comes from. The metal was later named cuprum in Latin, which turned to copper in English. Nowadays, the big copper-producing regions are in South America, Chile and Peru, the southern part of Africa, China and the US. And it seems that copper still has a bright future ahead of it, because of the transition to ever more electricity, to replace fossil fuels. This requires transmission and should sustain demand for copper, which remains the only affordable and efficient option for regular electric cables. For mammals like us human beings, copper is found in very small quantities in our bodies. But for some mollusks and crustaceans, it can replace iron in blood cells. Our blood cells, or the blood cells of fish too, use hemoglobin, which is a protein containing iron that facilitates the transport of oxygen in red blood cells. But some invertebrate animals don't have hemoglobin, but hemocyanin instead. These proteins can also bind oxygen temporarily to transport it, but with copper atoms instead of iron. This is why blood is not necessarily red. The blood of octopuses or horseshoe crabs is blue because of hemocyanin. Zinc is a metal that in some respect is chemically similar to its predecessor in the same group, magnesium. I already told you before about how different metals were obtained from ore by smelting or electrolysis, like in the case of aluminium. But how are these ores sorted? Because when ore is extracted from a mine, it is not pure, and from one site to another, the type of ore that is going to be taken from the ground, the elements it contains, can be very different. So the first step before the ore can even be processed is to separate it from rubble that will be useless. And there are different ways of doing this. It can be done by crushing and smelting, which is the usual treatment with iron ores. Another method, used especially for copper and precious metals or uranium, is called heap leaching. It uses a series of chemical reactions that absorb specific minerals, so that the one or the ones that are wanted are progressively separated and become usable. But the modern refining of zinc doesn't use these processes. It is achieved via another one called froth flotation. Froth flotation is a process that separates minerals from worthless materials by exploiting their hydrophobicity, how much they are attracted or repelled by water. You know what hydrophobic and its opposite, hydrophilic, means. A hydrophobic material is one that is repelled by water and will not get wet or mix with water easily. Oil, for example, is hydrophobic. Hydrophilic is the opposite. It gets wet or melts very easily in water. Table salt, for example, is a typically hydrophilic compound. So the concept of froth flotation is to apply different wetting agents to ore and filter it based on what floats and what doesn't float. And this way it is possible to create an industrial process that can separate automatically large quantities of raw materials. Raw material in the case of mining, but froth flotation also serves in other areas and processes, like for the treatment of used waters or in paper recycling. It is not limited to mining. The development and the industrialization of froth flotation in the 20th century enabled greatly the use of ores that were not rich enough before to be used. Many mines could simply not have existed without it, or they would have been way more expensive to operate, because the ore they produced was not rich enough to be exploited. So this is how zinc ore is typically separated. Then it is roasted at high temperature to purify it, because it generally comes associated with sulfur in zinc sulfides. And finally, when most sulfur is gone, it is put in a solution to be obtained pure using electricity, like for aluminium. Zinc is resistant to corrosion and also relatively light, which is why it used to be employed to cover roofs, it still is sometimes, or to make gutters. But it tends to be replaced in that role nowadays by plastics or other elements that can be even lighter and also resistant to corrosion. In biology, zinc is also an essential element to life, from microorganisms to plants to animals. Like for a few other metals, life has evolved on Earth using the properties of zinc extensively. So, like calcium or iron, you find it in a lot of bricks that are essential to biological life. It is present in every single class of enzyme. You remember what enzymes are? They are very important to life because they act as catalysts that make many chemical reactions necessary to life happen. Finally, in our immediate environment, zinc is also in brass. It's alloy with copper. Brass was already in use thousands of years ago, during the Bronze Age. It could work as a substitute to bronze when zinc rather than tin was available. Except brass is softer than bronze, so it is not as suitable for tools or weapons. When it contains relatively more copper, brass tends to be bright and gold-like. This is why it is often used for doorknobs or drawer pulls. You probably have more brass and therefore zinc around you than you think. It is also common in zippers, in plumbing, because it resists well to corrosion, or in electrical plugs and sockets. Let's move on to element number 31, gallium, and 32, germanium, which are used essentially in electronics. Their properties are somewhat comparable to aluminium and silicon, respectively, but they are way less abundant and harder to collect, which is why they are mainly used in small quantities for electronical applications. Both of them, gallium and germanium, are also called metalloids. So what is that? It is like the concept of semiconductor. Metalloids are elements that have some of their properties identical to metals and other properties similar to non-metals. They are in between. But we saw before that the concept of metal itself was imprecise, because what defines a metal, the capacity to conduct heat and electricity, could change with the conditions. Under certain conditions of pressure and temperature, many elements become conductive, even hydrogen. I mentioned before metallic hydrogen. that is thought to be present in large quantities inside gas giant planets like Jupiter or Saturn. And metallic hydrogen is just regular hydrogen made conductive, metallic, by extreme heat and pressure inside these planets. So the boundaries, the definitions of metalloids are also a bit imprecise. They lack specificity. But the term is still used in the literature of chemistry. And some elements are still often called metalloids. Among the ones we have already reviewed are boron or silicon. Sometimes other elements like carbon and aluminium are also included in the group of metalloids. But this is much more controversial, because many chemists prefer to consider them as a non-metal and a metal respectively. So, as you see, the concept of metalloid is not very specific and well defined. But if you come across it, the concept behind is that it is an element that has some of the characteristics of metals without being one. Element 33 is famous for its toxicity. It is arsenic, another metalloid, by the way. Arsenic as a poison has been known for centuries, thousands of years even, since antiquity. Actually, the name arsenic comes from a word in Syriac, a language that was spoken in the Levant 2000 years ago. It was adopted into Greek, arsenikon, then Latin, arsenicum. From there it became arsenic in French, and it passed to English as arsenic. As an element, it is used sometimes in alloys, not a recent use. During the Bronze Age already, there were cultures that added a bit of arsenic to their bronze to make it harder. And in industrial times, it was added to many products like insecticides, herbicides, or products to treat wood for its capacity to eliminate biological life. All these applications tended to decline in the past decades as the toxicity of arsenic was progressively recognized. Arsenic poisoning can be quick if a massive dose is ingested, or progressive over a long period of time if someone is constantly exposed to even small doses. It is very potent. But why is it so toxic? Because arsenic oxides have an affinity with compounds that are situated at the active sites of many enzymes. It disrupts the correct functioning of cells and leads to their death. So the signs of an arsenic poisoning are not very specific. The death of cells causes multiple organ failures. That's why, until the Middle Ages, arsenic was the poison of choice to discreetly kill people. It was impossible to say what the exact cause of death was. Poisoning would be suspected, obviously, but it was impossible to prove. Later, tests were developed, and arsenic poisoning can now be identified easily. But the bad reputation of this element for health was established, and rightly so. Element number 34, selenium, is also toxic in small doses. Trace doses of selenium are necessary for cellular function in many animals, including humans, but the level of toxicity is low. However, selenium is less abundant than arsenic, and that's why poisoning is very unlikely, except near places where it can bioaccumulate, in some aquatic habitats, for example, near chemical plants or because of farming. In these cases, selenium may accumulate in plankton or fish, in wetlands or ponds, and become dangerous if the fish are consumed by humans. Number 35, bromine, is the next element after fluorine and chlorine in the same group called halogens. I already told you about fluorine and chlorine. One particularity of bromine is that at standard conditions for temperature and pressure, it is a reddish-brown liquid. A particularity because out of 118 elements, there are only 2 that are liquid at normal conditions: mercury and bromine. Of course, there are plenty of liquids around us, starting with water, but these liquids are compounds or molecules. If you separate water into oxygen and hydrogen, these 2 elements at normal conditions will be gases. Number 36 is krypton, yet another rare gas after the ones we already discussed: helium, neon, and argon. Like them, it is a colorless and odorless gas that occurs in trace amounts in the atmosphere, and it is used in fluorescent lamps for the same reasons as its predecessors. Like other noble gases, it is very little reactive. After krypton, the following elements also share properties with their respective cousins of the same groups. Rubidium, number 37, is the following alkali metal, like potassium, sodium, and lithium. One difference it has with them is that it is denser than water, so it doesn't dissolve in it that easily. Instead, it tends to sink in water. Then there is strontium, number 38. Natural strontium is mostly not hazardous to health, because naturally it is found as a stable isotope, strontium-88. You remember, 88, this means that it has 38 protons in its nucleus. It is element number 38, plus 50 neutrons, for a total of 88 particles. But there is one isotope, strontium-90, with 2 more neutrons, and it is a dreaded product of a nuclear fallout. Strontium-90 appears as a result of the fission of bigger atoms, the fissions that provide the energy for a nuclear reaction. And strontium-90 is highly radioactive, which in other terms means that it is unstable. Strontium-90 nuclei are not energetically comfortable with their 52 neutrons, and this is what makes elements radioactive. Because they are not perfectly stable, they will tend to expel particles, energy, or even fission into 2 or more smaller atoms. What we call radioactivity is this behavior, this property of emitting energy and particles spontaneously. We will elaborate on that when we cover other elements. But strontium-90 is bad news, because on top of being radioactive, it is easily absorbed by the human body, in a similar manner to calcium, which is its predecessor in its group. And that's why this particular isotope, strontium-90, is particularly dangerous in a nuclear fallout. After strontium comes element number 39, yttrium, which I already mentioned as a rare earth element. It is used in LEDs and various industrial applications, like the production of electrodes, of lasers, or medical applications. Number 40 is zirconium, a metal that is used either as an additive to metallic alloys for its resistance to corrosion, or as a refractory, that is to say, for its resistance to heat. Element number 41, niobium, is little known, and you may never have heard of it, but it is critical to many technologies. It is incredibly resistant to heat, with a melting point close to 2500 degrees. That's almost 1000 degrees more than iron. It is not the highest melting point of all metals. We will see that later, but it is considerably high. And it is used in jet and rocket engines for that property, as well as plenty of applications in very small quantities, optics, electronics, in the nuclear industry. It can serve in alloys to coat coins as an alternative to nickel. So we are surrounded with it, and we use it every day in very small quantities, but we barely know of this element. Its followers are also little known. Number 42 is molybdenum, another element with a very high melting point. It is used in alloys for that reason. Technetium, number 43, or ruthenium, 44, are rare metals. They are used also in very small quantities in very specific applications in nuclear medicine or as catalysts. Only a few tons are consumed annually in the world. The next one, number 45, is more famous. It is rhodium, one of the rarest and most valuable precious metals. In recent years, the ounce of rhodium traded around $15,000. This is 7 times higher, 7 times more expensive than gold. But why is rhodium so sought after? There is a minor use for it in jewelry, very rarely to make pure rhodium pieces. Not so much because of the price, because even at 7 times the price of gold there would still be buyers. It's also because rhodium is really hard to work with. It has a very high melting point, and it is not malleable like gold. So it is used, generally plated, on white gold or on platinum, to give these metals extra shine and a white surface, at time of sale only, because after this thin layer of rhodium will wear away with use. But jewelry is a small application for rhodium. A much larger quantity is used as a catalyst in automobiles, in catalytic converters. And there is no cheaper alternative to rhodium for that. Another rare and useful element is number 46, palladium, but the following is way more famous. It is number 47, silver. Silver has the reputation to be a precious metal, even though less so than gold. And indeed, if you look at the prices to put things into perspective, it is far less expensive than gold. So I told you that in recent years, 1 ounce of rhodium was worth $15,000. 1 ounce of gold $2,000, and silver is around $22–23 per ounce, almost 100 times less than gold. Silver is another metal that has been used since antiquity, together with a few other metals, gold and also copper, iron, tin, zinc, lead or mercury. If it was more abundant than it is, silver could have a massive industrial use and even replace copper. Because of any metal at normal conditions, it has the highest electrical conductivity and thermal conductivity. So, in theory, silver electric cables could work even better than copper cables. But this would not be feasible because there is just not enough silver available. And by weight, silver is dozens of times more expensive than copper. So, technically or financially, it could not replace it. We can go fast on the three following elements: 48, cadmium, 49, indium, and 50, tin, because their properties are similar to their predecessors of the same groups in the table. I told you about tin already when we discussed the alloys of the Bronze Age. The same can be said of antimony, number 51, tellurium, 52, and iodine, 53. But let's stop for a minute on the following one, which is xenon, number 54. Xenon is yet another noble gas, and it has an isotope, xenon-135, that is closely monitored in nuclear reactors. But why is that? Xenon-135 does not occur naturally. It is too unstable, too radioactive to last. It is an isotope that appears in nuclear fission reactions. Of the different elements that are created when nuclear fuel fissions, typically this fuel is uranium, an isotope of iodine, iodine-135, is a common one. And this product of nuclear fission, iodine-135, experiences a form of radioactivity called beta decay. I told you before that radioactivity was like an umbrella term for different phenomena that so unstable atoms emit energy and particles. Beta decay is one of these phenomena, a type of radioactive decay in which a nucleus emits an electron and at the same time a neutron becomes a proton. So, if there is a change in the number of protons, the atomic number changes, it is no longer the same element. And I just told you that iodine was number 53 in the table, with 53 protons. If it acquires one more, it becomes element 54, xenon. Iodine-135 and xenon-135 have the exact same number of particles in their nucleus, except xenon has one proton more and iodine has one neutron more. So, as you understand now, xenon-135 is like a subproduct of fission. Iodine-135 appears first, and it transmutes into xenon-135. But why is it relevant to the management of a nuclear reactor? Because this xenon-135 isotope has one characteristic. It is neutron hungry. It tends to absorb more neutrons. And in a nuclear reactor, that's a problem, because it is the flow of neutrons that keeps the fission chain reaction working. The circulation of neutrons makes them available to be absorbed, caught by heavy atoms like uranium, which increases their instability and makes them fission, releasing more neutrons, and so on. The reaction sustains itself as long as there is fissile material available. But if you have xenon-135 eating too many neutrons, that can slow down and even stop the chain reaction. This is a well-known problem when operating a nuclear reactor. At the start, the reactor contains no xenon, but as more and more fission reactions happen inside it, in its first hours of functioning, xenon-135 piles up in the reactor as a product of fission, and it starts stealing the neutrons, which inhibits the chain reaction and will even stop it if nothing is done. So a nuclear reactor that would be turned on and left to its own device would stop by itself after a while. That's a phenomenon called xenon poisoning, and it is well known by nuclear reactor operators. In order to avoid xenon poisoning, the period when a reactor enters or re-enters service after fresh fuel has been loaded, or after a technical stop, this period is closely monitored to avoid xenon poisoning. By compensating the negative impact of xenon on the chain reaction with actions that stimulate fission, like withdrawing the control rods that also inhibit fission inside the reactor. And after a while, as xenon-135 disintegrates, an equilibrium is found between the creation and the destruction of xenon-135 inside the reactor. So the quantity remains stable and doesn't prevent the reactor from working. It just becomes one variable of its normal functioning. Xenon poisoning was an important factor in the chain of errors that led to the Chernobyl disaster in the 1980s. The operators of the reactor that eventually melted lost control of it because they tried to stimulate the reaction inside, not estimating correctly that the reactor was poisoned by xenon. They knew of this phenomenon, and in normal conditions of use, the reactor and all the rules and processes to operate it were designed to manage it. But they were making an experiment on the reactor, and they willingly removed several securities that were strictly forbidden to remove. They violated the rules of operation, and they saw the flow of neutrons lower than they wanted inside the reactor. So to stimulate it, they withdrew the control rods too much, and in seconds, xenon poisoning was overcome. The chain reaction grew exponentially, and the reactor became so hot that before they could react, the control rods were expelled, all control was lost, and the energy generated by the reactor reached hundreds of times the operational limit. Following an explosion, a chemical explosion, that broke the building that contained it, the reactor and its radioactive material were exposed to the outside. A huge volume of particles were ejected, radioactive particles, in the atmosphere, and the inside of the reactor's tank began to melt. that's another story. But Xenon-135 played a part in it. Staying with highly radioactive isotopes, we have cesium, element number 55, which also has an isotope, cesium-137, that is a hazardous fission product. And after that, we have element 56, barium, a metal with very few applications. It is used sometimes as a radio contrast agent for X-ray imaging. It is also added in superconductors and some steel alloys. Elements 57 to 71, from lanthanum to lutetium, are called the lanthanides, and I told you about them already when I spoke about rare earth elements. They are all parts of this group, and chances are you never heard their names, because they are never mentioned individually out of labs or industrial plants. They include names like neodymium number 60, promethium number 61, europium 63, or ytterbium number 70. Number 72 is hafnium, and hafnium is also a rather confidential element, but one of its applications is as a neutron absorber, a neutron catcher, in the nuclear industry. I just told you about Xenon-135 absorbing neutrons. Hafnium also has that capability, and this is why the control rods of nuclear reactors that are driven inside the reactor to slow it down or withdrawn to stimulate it generally contain hafnium. It slows down chain reactions. Number 73 is tantalum, an element very similar to niobium that we covered before. They're from the same group, the same vertical line in the table of elements, and they share properties. Like niobium, tantalum is highly refractory. It resists to heat, and its melting point is the highest I have mentioned so far, 3000 degrees Celsius, or 5400 degrees Fahrenheit. That's twice hotter than for iron and 3 times copper, so it is really hard to melt. But it is not the highest of all elements. The highest known melting point belongs to a more famous metal, element number 74, tungsten. Tungsten melts at 3400 degrees Celsius, and of all elements, it also has the highest boiling point, temperature at which it turns to gas. This boiling point is almost 6000 degrees Celsius, more than 10,000 degrees Fahrenheit. Tungsten is hard and dense. We rarely get a chance to manipulate tungsten, but to give you an idea, it is 1.7 times denser than lead, so it feels really heavy, and this density plus its hardness is the reason why it is suitable for military applications, especially for penetrating projectiles. The tungsten head is a good choice to pierce armor. A more famous use of tungsten, but it is disappearing in our homes at this point, was for light bulb filaments. For most of the 20th century, light bulbs used filaments, generally of tungsten, for its high melting point. The electric current in the filament made it heat up and emit light. The inside of the bulb was filled with a noble gas, typically argon, to avoid combustion, for reasons that you now understand, because noble gases are very little reactive, and the atmosphere inside the light bulb was free of oxygen to avoid combustion of the filament. Element 75 is rhenium, one of the rarest elements in the Earth's crust, about 1 part per billion, which in other words means that to find 1 gram of rhenium you would have to process, in average, 1,000 tons of Earth's crust. It has a few industrial applications, especially for jet engines, because it serves in superalloys with nickel to make combustion chambers. The 2 following elements, osmium, number 76, and iridium, number 77, are famous for their density. Osmium is the densest element known among the ones that occur naturally. It has a density of 22 grams per cubic centimeter. For comparison, this is 3 times more than iron, and twice more than lead, and 22 times more than water. Water is the benchmark for density. So what it means, said differently, is that for the same volume of water and osmium, the block of osmium would be 22 times heavier. Osmium is also even rarer than rhenium, and is estimated to be the rarest of all precious metals. So you could think it is going to be extremely expensive, but not that much, because it has very few applications. It doesn't look particularly shiny. It is just silvery, like many metals, and so the price per ounce, when there is one, because there are very few transactions, is between 1/3 and half the price of gold. Iridium is a bit more frequent, but still confidential. World production and consumption of iridium is around 7 tons per year. That's really not much. But their follower, number 78, is way more famous. It is platinum. In monetary terms, platinum is less expensive than gold nowadays. But there was a time when it was up to twice as expensive, and it remains a precious metal that looks silvery white. It has more industrial applications than gold. And its most remarkable characteristic is that it is one of the least reactive metals. These metals that do not react easily will often be found pure in nature, which is logical. They did not combine with others. Gold and others we already reviewed, like rhodium, palladium, and osmium, have the same characteristic, and they are sometimes called noble metals because of it. Noble in the sense that they are lowly reactive, like for noble gases. And gold is the following one, number 79. Some of the characteristics that make the appeal of gold, like its absence of corrosion, so it remains shiny, come from its low reactiveness. It is also resistant to most acids. There is the exception of aqua regia, this mixture of hydrochloric and nitric acid that we talked about earlier. And gold is relatively rare, but there are many rarer elements than gold. The high monetary value of gold comes from the combination of its visual appeal. It doesn't get dark because of corrosion. It is yellow, contrary to many metals that are just grey, and it has built up a reputation, an aura as a precious material after several thousand years of being a symbol of wealth and power around the world. It didn't happen in every single culture, but in many of them, from America to Africa, Europe and Asia. Everywhere, gold acquired a particular, a specific status, enough to make it an ultimate symbol of value. And 90% of demand for gold is linked to this. 50% of produced gold goes to jewelry, 40% as a reserve value, as an investment, bearing in mind that a part of the use in jewelry is also intended as a mean of stocking value. And only 10% goes to industry, mainly for electronics. There is a bit in all computers, for tooth restoration, or gold leafing of ornaments. We still have a few famous elements to go through, like the following one, number 80, mercury. I told you earlier that bromine and mercury were the only two elements known to be liquid at normal conditions. Mercury is the only metal, because bromine is not a metal. And it has various uses that are familiar, like inside thermometers. But it is also known as an environmental heavy metal. Heavy metal is another concept that is loosely defined. It can refer to the density of metals, as opposed to lighter metals like aluminium, and in that case, mercury is a heavy metal. It is pretty dense. But in health and environmental terms, heavy metals are elements that can be highly toxic, either pure or as parts of compounds, and that accumulate in the environment or in the food chain. Mercury is one of them, together with lead, chromium, arsenic, cadmium. I already highlighted the toxicity of several of them. Mercury in particular can cause damage to the central nervous system. And another highly toxic element when it comes as salts is thallium, number 81, often used in history as an alternative to arsenic to poison people. Thallium is sometimes called the poisoner's poison or the inheritance powder for that reason. Number 82 is also toxic and another heavy metal that has probably killed on a much larger scale than arsenic and other toxic elements I mentioned before. It is lead. Lead was historically relatively easy to retrieve and abundant. It has a high density. It melts at a very low temperature, just a bit more than 300 degrees Celsius, so it made it a metal of choice, not too expensive, easy to use, for a large range of applications in construction, plumbing, paints, batteries, as an additive to gasoline. Its toxicity has been known since at least the ancient Greeks and Romans, who documented it. It caused a syndrome called Saturnism, but it was downplayed for a long time. I remember when I was a kid, there were still applications for toys, like little soldiers or figurines, or plumbing, that must have been forbidden now, but were common in the 1970s and 80s. Because lead is a potent neurotoxin that damages the nervous system and accumulates in bones and soft tissues. It is not spectacular, but over time it affects general health. It attacks the heart and kidneys, and what it is most known for, it causes neurological disorders. Element 83 is bismuth, a metal that can be sometimes used as a replacement for lead because it is way less toxic. And after that, with element number 84, polonium, we enter the territory of heavy atoms. The more we advance, the more protons they have, and also the more neutrons they tend to have in their various isotopes. So they are heavier and heavier. Heavy atoms that have a tendency to be unstable, that is to say, to decay, to emit particles and rays. I mentioned earlier the radioactive beta decay, with the example of iodine-135 turning into xenon-135 in nuclear reactors. Beta decay is when an atom emits an electron, or its opposite, a positron, and a neutron becomes a proton. Another type of radioactive decay is alpha decay. It is when the nucleus emits what is called an alpha particle, or a helium nucleus, 2 protons and 2 neutrons. Instability of an atom may lead to radioactive decay or even to fission, when the nucleus breaks apart into 2 or more atoms with a smaller atomic number, of course. So, under the umbrella of radioactivity, we have different phenomena that happen at the atomic level and lead to the emission of radiations, of energy like heat, and particles of different nature and sizes. It can be protons, neutrons, electrons. From polonium and after, all atoms have varying degrees of instability. Sometimes it is not very pronounced, and they decay very slowly, over millions of years. Other times, they are very unstable. This depends on the elements and their respective isotopes. But contrary to lighter elements that we have just gone through, that can have radioactive isotopes and other isotopes that are not radioactive, above atomic number 83, 84, everyone is radioactive to an extent. And it begins strong with polonium, which only has highly radioactive isotopes. The discovery of polonium in 1898 is one of the discoveries that made the fame of Marie Curie. This is why it is called polonium, after Poland, her country of birth. She became the most prominent of the early explorers of radioactivity, a phenomenon that was barely understood in the 19th century. Element number 85 is astatine, which is the rarest naturally occurring element of all elements in the Earth's crust. Why is it so? Because it appears only as the decay product of heavier elements when they lose protons, and all of its isotopes are also short-lived. The most stable one has a half-life of 8 hours. half-life is a concept used to illustrate the radioactivity of elements. It is the time it takes for half a quantity of radioactive material to decay. So a half-life of 8 hours means that in 8 hours, half a given quantity of an element will have decayed. That is short. The half-life can range from seconds to millions of years. The shorter, the more unstable and radioactive an element is going to be. So the consequence of this instability is that no solid sample of astatine has ever been observed. Even if one could be gathered, it would be immediately vaporized by the heat of its radioactivity. So we don't know what astatine would look like at normal conditions, because it cannot really exist as a solid at normal conditions. After astatine comes a new noble gas, number 86, radon, which is also radioactive under all its isotopes, contrary to its predecessors in the group of noble gases. The longest half-life of the natural radon isotope is almost 4 days, but that remains short, and any radon in a lab has to be synthesized, obtained by decay of heavier elements or another method. After it come several more radioactive elements: 87, francium; 88, radium, another discovery of Marie Curie; 89, actinium; 90, thorium, which is more stable than its neighbors in the table. It is still radioactive, but it has one isotope, thorium-232, so that's 90 protons plus 142 neutrons. That has a very long half-life, a half-life of 14 billion years, about the estimated age of the universe. So this particular isotope is only very lightly radioactive, enough to not be dangerous to humans, and it has a few industrial applications. Number 91 is called protactinium, and after it come the two last elements of the table that have a degree of fame. Number 92, uranium, and number 94, plutonium. In between there is neptunium with number 93. Uranium is the fuel of choice for nuclear power plants and weapons. But why is that? Because some isotopes of uranium, essentially uranium-233 and 235, can maintain a sustained nuclear reaction when they are in sufficient concentration. And their fission is the one creating all the subproducts that appear in the reactor. And uranium was present naturally in sufficient quantity on Earth to have a functioning industry based on it. Even though natural uranium available in nature is another isotope, uranium-238, which needs to be processed, enriched in uranium-235, before it becomes usable nuclear fuel. Because uranium-238 is not prone to fission that easily. Plutonium, number 94, is the last element that can occur naturally without human intervention, but in very small quantities, and all the plutonium used is obtained artificially via the transformation in nuclear reactors. The exact term is transmutation of uranium atoms. They only need to gain 2 protons to become plutonium. That is what also made the appeal of uranium for military use in nuclear weapons. Uranium is said to be fertile because it can be turned into plutonium, and plutonium is particularly prone to participate in fission chain reactions. Some of the first atomic bombs already had plutonium cores. After plutonium, all elements from 95, which is americium, to 118, oganesson, had to be obtained completely artificially after their properties had been theorized. As far as we know, the conditions for their creation do not exist in nature, and they have been synthesized and classified for the sake of fundamental research because they have no significant applications. They are very unstable. These are huge atoms with hundreds of particles. So, to conclude our talk for tonight, I will go through their numbers and names. It's a bit like counting ships. Let's go. So we have number 95, americium, 96, curium, 97, beryllium, 98, californium, 99, einsteinium, 100, fermium, 101, mendelevium, 102, nobelium, 103, lawrencium, 104, rutherfordium, 105, dubnium, 106, seaborgium, 107, borium, 108, hassium, 109, meitnerium, 110, darmstadtium, 111, oranginium, 112, copernicium, 113, nihonium, 114, flerovium, 115, moscovium, 116, livermorium, 117, tennessine, 118, oganesson. We have finally completed our tour of the periodic table of elements, and I hope you enjoyed this little exploration journey of the elements. I'll be back soon with another story, one of historical mystery, and in the meantime, sleep well, sweet dreams, au revoir.